Hello. Let's continue with strength of figure. So the strength of figure is a factor to be considered in establishing a triangulation system to maintain the computations within a desired degree of precision. It plays an important role in deciding the layout of a triangulation system. So how do we compute this strength of figure? So we have here the formula, where D is the number of directions observed excluding the known side of the figure. And we have delta A, delta B, and delta C here. The deltas in here in this formula. The difference per second in the sixth place of logarithm of the sine of the distance angles A, B, and C respectively. So you will see that later in an example. Okay. So the distance angle is the angle in a triangle opposite to a side. Okay, that's self-explanatory. Now C in the formula is the number of geometric conditions for side and angle to be satisfied in each figure. It is given by C is equal to n prime minus s prime plus 1 plus n minus 2s plus 3. Now n is the total number of lines, including the known side in a figure. We just have to count these lines. Then n prime, the number of lines observed in both directions, including the known side. Okay? So in both directions, because there are also lines that are observed only in one direction. So we are talking here about the lines observed in both directions. We have S, the total number of stations, and S prime, the number of stations occupied, because as we've said before in the previous video, not all of the stations can be occupied, right? Okay, let's do an example. We have here a quadrilateral ABCD with the baseline of AB, so we know the length of AB, and our common side AD, and the required side is DC. Now the common side means that we're going to use this side in computing for our required side. So this is only one route because we can also use, so we are using this one, right? AD as our common side, but we can also use BD, and also we can also use AC as our common side, and we can also use BC. Now for this example, we will be computing for R, center figure, for when we use AD as our common side. And then we will then compare the different values for R for different common sides. And then the goal is to select the smallest value for R, because the smaller the R, that means the more stable that particular route is. So you will use that for computing the length of your required side. So for this example, in computing for the strength of figure, we will not the baseline length will not be required. Okay, so let's start with the d minus c over d part. We will calculate the value for the deltas later. So d is the number of directions observed excluding the known side of the figure. Now, as you can see here in the quadrilateral, we have here arrows indicating the directions observed. Okay, so if we take a look at our baseline, it's observed twice. It's observed in this direction, right? And also in this direction. So it has been observed twice. Okay, so let's count the number of directions observed. So we will not include here the two directions for the baseline. So we have 2, 4, 6, 8, 10. So our D here is 10. Yeah. Then what is our C? So let's compute for C. So what is the formula for C again? Let's write it out. C is equal to n prime minus s prime plus 1, then plus n minus 2s plus 3. Okay, so what is n prime again? The total number of lines, including the known side of the figure. Okay, total number of lines. So 1, 2, 3, 4, 5, 6. So we have 6 here. Minus s prime. So what is s prime? The total number of stations. So how many stations do we have? We have 4, right? And then plus 1. And then n. So what is n? The number of lines observed in both directions, including the known side. Number of lines observed in both directions. So in our figure, all of the lines are observed in both directions. So we have here a value of 6. Minus 2 times s. So what is s? The number of stations occupied. And in this figure, we're also assuming that all of the stations are occupied. So we have 4 here as well. And 2 times 4, and then plus 3. Okay, so let's calculate the value for C. We have here 6 minus 4, that's 2 plus 3. And then plus, we have 6 minus 8 at negative 2 plus 1, that would be negative 2 plus 3, that would be 1. So we have a value of c is equal to 4. So we have here 10 minus 4 all over 10. So what do we have? We have 0.6 as our value for d minus c over d. Okay. So now it's time. So let's erase this value. Let's erase this. Let's just to make some more space that we can still see the figure. Let's just write it down here. D minus c over d is equal to 0.6. Okay. Okay, so let's calculate the deltas. Let's start with triangle ABC. Okay. So what will be the distance angle that we'll be using here? So you will use the distance angle opposite the baseline. This will be distance angle. AB. That would be 44 degrees, right? And then distance angle AD be equal to 44 degrees as well. So that's convenient. Now let's calculate for the delta. Let's say for delta AB. So based on the definition, we're going to do log sine of 44 degrees, 0 minutes and 1 second minus log sine of 44 degrees, 0 minutes and 0 seconds. Okay. Now if we calculate that, you will get 0.00000021803.182, and then you will use 2.1803182. Okay, so the sixth place, right? Remember the definition: 1 2 3 4 5 6. The definition says the sixth place. Now you might be asking, why do we have to use this log sign? So it turns out historically they use log sign in the field. So this was before calculators were even invented. And then they use tables. Now it is easier to use addition and subtraction instead of multiplication and division when you're doing things manually. So they use this log sign. Now, why do we have to use this sixth decimal place? Because as you will see later, we will be comparing the values of r. Now, if we're just comparing them, so why not use the simpler 2.1803182 instead of the 0.0021, right? So it will be easier in calculations. Okay, so let's use that. So since the distance angle AD also has the 44 degrees, then we can now compute for delta AB squared plus delta AB delta AD plus delta AD squared. So if you compute that, you will then get 14.26. Okay, so let's just write it down here. Let's just copy this here on the side. Okay, so let's do another one. Let's do for triangle ADC, right? So let's do triangle ADC. What are the distance angles that we'll be using here? Distance angles that we'll be using are, let's just erase this first. So distance angles we'll be using are AD again. Distance angle AD here is equal to 30 degrees, right? For this triangle ADC. 30 degrees, and distance angle DC will be what? That will be 38 degrees. So let's calculate the log signs again. So delta AD will be log sine of 30 degrees, 0 minutes, 1 second minus log sine of 30 degrees, 0 minutes and 0 seconds. Okay, so you will get, for this one, 0.0000364,68456. Okay, and now we will use ED is equal to 3.6468456. Okay, and then um, delta AD, I mean DC, delta DC. Delta DC will be, so it's the same thing, no? Instead of using 30 degrees, you just use 38 degrees. So you subtract the 1 second difference, then you will get here 2.694928. Okay, so that is our delta DC. Now, if we calculate this again, we calculate delta AD squared plus delta AD multiplied by delta DC plus delta DC squared. We will then get 30.39. Okay. Okay, so let's set this aside again. Okay. So now we will take their summation. Okay, let's go down here. The summation, their summation will be 44.65. Okay. Now, so if we calculate our formula, so the strength of figure will be 0.6 multiplied by 44.65. Now, R will be 26.79. Okay, this is our R. Okay, now the next step is, now that we've successfully computed for R using this route, and you will then calculate R for the other routes and you'll compare. Okay. Okay, so let's compare the R. So we've used common side AD right here in the top left, right? We have 26.78, okay, or 79. And then if we compute for using the other lines as common side, you get R 13.72, and then R 6.39, R is 18.92. So the smallest is R is equal to 6.39 if we use the common side is BD. So we will use BD here as the our common side in computing for our required side. Okay, so that's how you use the strength of figure. And that's all for this video, and I hope you learned something, and I will see you in the next video.